So now, today we discussed about that power, what are the power converters it may required in the electric vehicle design domain. So previously we have calculated that how much is the motor power for the exact vehicle, whatever vehicle movement. So now if you go in detail, so what are all the power converters are available? How what is it's a typical rating? What all it's a typical rating, right? So let us check one by one. See, actually, initially that we may require the power converter in the charging station, right? So that I mean for that power converter, the input will be like either a wind or solar or the grid source. Output, as per the battery requirement, we have to build the circuit, right? So see here, the typical ratings is about input is to 440 and then output is based on the battery rating we may have. You can get it. And the same way for the onboard charger. So here also the similar model, like input is the 440 and then output is about the as per the battery requirement. And then the third power converter is that inverter drive. So here the input is the battery input. Output is the as per the motor terminal information. As per the motor terminal information, right? And next one is that power supply. So this power supply is for additional other than the fundamental components, like other essential components like infotainment system, sensor models, and other information. See here, generally for this one, so in the EV, the people will keep it as a secondary battery. Generally, in the EV, there are the two kind of battery. One is that primary battery, and another one is that secondary battery, right? So here, this additional power supply will work for the secondary battery, right? And so now, so if you take a EV charging station, see here, this is the level 1 charging stations, or else the residential charging station. Typically, it will be like a 2.2 kilowatt, 2.2 or 1.2 kilowatt is the maximum limit. And level 2 charging station, it's called the commercial charging stations. So it up to 20 kilowatt, you can, the people are designing now. Sometimes the 33 kilowatt, 65 kilowatt, or else the string-based charging station also people are planning. And then the level 3 charging station or fast charging station, it can deliver up to maximum 400 ampere, right? So it can deliver up to maximum 400 ampere. And then vehicle to grid to vehicle. So this is again conceptual wise the people are working. So here maximum 2 kilowatt is the transferable power, right? So this is the some typical power, typical rating of the EV charging stations. Just a second. Yeah. So now, see here, if you go in detail about the onboard charger, so as I mentioned earlier, input to this OBC model is the grid, right? And then, uncontrolled AC to DC rectifier, and along with power factor correction also may require, because so if you develop any power converter, then the power quality of the power converter is very important. And second model is that voltage regulation, and then current regulation is again it's another important parameter. So you have to consider all those information, then only you can develop your power supply circuits. And finally, that isolation, DC to DC converter to regulate the high ripple free power supply, right? This is the onboard charger block diagram. So now let's go in detail. So see here, this is the AC uncontrolled rectifier, right? And this is the power factor correction circuit, right? So why it is required and all, this is the session we listed, and we'll check one by one. So just engage with the entire session so that you can easily understand what is happening inside the session, inside the block. And so this is the high frequency DC to DC converter to reach that ripple free pure DC voltage, right? And push pull rectifier, say from DC to DC converter, high frequency, this will act as an inverter. This is the high frequency transformer, and push pull converter will again convert the DC. So this DC will be highly ripple free power to the battery, right? So now let us check one by one. So what is the power factor? How it can be analyzed? So I'm just going to open this MATLAB. Yeah. So I hope you all are available with MATLAB installed laptop. So please parallelly follow the session. Yes. So now let us take one small DC AC to DC rectifier. So I'm just going to take a AC voltage controller and universal bridge. So this is the universal bridge. Take a two leg so that we can work it for the single, single phase. And this is the diode block, not uncontrolled. Yes, yes, correct. See now I'm going to take RLC like a resistance just to change use that R. I will tell you how to model the resistance. Just engage the entire session and take a voltage and current measurement block, and then this is the output voltage, and same way take a current measurement block. Take a current measurement block. Again, let us take a current measurement block. So I'm configuring that this is the peak amplitude. See, now we know only about that RMS voltage, right? So RMS voltage is the 230 voltage. So what will be the peak voltage? Participant, just comment. What will be the peak voltage for the 230 voltage as RMS voltage? Anybody, can you just comment? What will be the peak amplitude of the 230 voltage RMS? Participants, can you just comment? Yeah. So here square root to SQRT of 2. So this is the peak amplitude of the 230 voltage RMS, right? And then now we have to get a so just to take a go to function, and yeah, so this is the VS, like a voltage source voltage, and then this is the source current, right? Source current. And a similar way, take again go to function. Yes, thank you, Professor Srinivas. And this is the V naught, and the same way this is that I naught, right? Yes. So now, so the 230 is the RMS voltage, 230 divided by 5 ampere. So this is the typical load. We are trying to draw 230 voltage and then 5 ampere from the rectifier. So this is the resistance model. So here, if you change the 5 value, then similar way, suppose if you draw 10 ampere, then the source will support you 10 ampere, right? So now we build a 5 ampere as the load resistance, right? So now, yes, so now take a so now let us take a current, input voltage and input current, and the same way output voltage and then output current. So take a scope block. I hope if you follow the things, then you can easily understand what and how we are trying to build the model. So just please follow the instruction, and then that's why I'm going very slow. Let us change the design so that you can easily view the data. So I'm just going to change the like number of lines so that we can easily view the data in very proper manner. And now power guide block, of course, we may require the power guide block since this is the Simulink components, right? Yeah, some power system components. So we may require the discrete block, right? For participants, if you have any questions, please raise. So now we just modeled uncontrolled rectifier, right? We modeled just uncontrolled rectifier. We are trying to implement like what is the observation from the from this one. Yeah. So now let us try to run this one for just 1 second. See here, we have observed that so the first graph is the input voltage and input current, right? And the third graph is the output voltage, and fourth graph is the output current. So now the point is that input voltage and input current both are in phase, right? So there is no any phase deviations, right? At the same time, the output voltage is floating from 0 to maximum, right? So that is not viable to apply this voltage in the EV battery. So now to that, to address that issue, now we are, So we are trying to increase the output voltage as like this, right? So this voltage we cannot apply, we cannot feed to that by EV battery because the battery needs a highly ripple free battery. So this was supply almost having 90% ripple, right? So there is no any average voltage. To increase the average voltage, what we have to do? So we have to increase the capacitance across this one. So instead of that, just to take a 1000 microfarad capacitor, right? So now if you run this one, now you can check, yeah. So now you can check that so input voltage is as per the sine voltage, and whereas the output of the input current is highly disturbed. It's not, even though if the phase, even whenever the input voltage is crossing the zero, at the same time, input current also it's getting crossed, but it's not a in phase one. It's not a in phase one. So what, instead of that, what we have to do? So we have to get a properly pure sine waveform, even in the input current side also. So this is why that input, power factor, your power supply generating a very poor power quality power supply, right? So to avoid such kind of issues, to avoid whenever the capacitor, filter capacitor gets charged, that time only the current, input current will get dropped. So rest of the time the capacitor will supply a current, right? So this will lead the discontinuous mode of conduction in the output side. But always we may require a continuous current. Always we may require a continuous current. So for that one, what we have to do? So we have to do the power factor correction into the block. So let us check one by one, right? So people are anybody facing the issue in your research, such kind of issues. See, if you are going to design any power supply, so you should worry about the two things. One is that input power quality, and output. Next one is that the load regulations. So if we try to draw like a 10 amp, 10 voltage or 30 voltage or 400 voltage or 500 voltage, exactly we should draw 400 voltage from the converter. All right. So that is a voltage regulation of the converter, DC to DC converter. So now let us check one by one. So again, we'll take a see, in the presence of the very poor power factor, we may require a high density power card. So that leads the heat issues in the charger also. So to avoid, if your input power factor has been corrected, then you may get a very less diameter, conductor size cable also you can use it. So to implement the power factor corrections, see here, instead of final, this is the final load. So this is the final load, and this is the DC to DC converter. And between this one input source, input rectifier, and then output converter, we may require a power factor correction circuit, right? So people, participants, do you have any questions? If you have any questions, just open the mic and then please ask. I'm here to help you in all possible ways, right? So now, so what do you mean by power factor correction? So simply, if your power circuit having the input current follows the input voltage character, then that is called a pure or unity power factor control, unity power factor controlled power supply, or else it will be either leading power supply or lagging power supply, right? So this is the simple circuit of the power factor correction. See here, this is the uncontrolled rectifier. Up to this one uncontrolled rectifier, here we are trying to implement one boost converter. So what will happen? So sometimes if the switch S1 is closed, then the inductor will get short circuited. By the time the inductor current will get inverter. So the inductor will try to store the current, and after that will release the switch. Then the inductor will supply a current to the load, right? So by keep on doing this operation frequently, then we can extend the power supply. We can supply the current without discontinuous mode. At the same time, the input voltage and current will get synchronized. So this simple method we are trying to implement. For that, we may require the proper design of the boost converter. So this logic is common to applicable for wherever. So now we should know how to design a boost converter, right? So for the boost converter, you may require some typical components. One is the bridge rectifier for the rectification, and then inductor, capacitor. So inductor for the boost purpose, as well as that power factor correction circuit. and one of the capacitor used to filter the component, filter the ripples. And third one, final one is that MOSFET. Of course, we may require any one solid state switches, right? So when S1 is closed, then inductor will get short circuited. By the time the current will get stored into the inductors. When you try to release the S switch, then the voltage will apply to the load, and the current inductor will take care about the continuous conduction mode of the current. So now, so let us take a design calculations. See here how we can first we should know the specification of the boost converter. What are all the specifications? So if you want to develop any one like 1 kilowatt 1 kilowatt DC to DC converter, what are all your basic information you may require before starting into the design? Participant, can you just comment? And second one is that efficiency. What are all the efficiency you may require? Maximum efficiency. So all the components will not work in the ideal efficiency. So here we have to fix the efficiency, and then range of input. Of course, in our system, the grid system, the grid is not a stable grid. Always it will fluctuate. So what is the maximum fluctuations in your area? Participant, can you just comment? What is the maximum fluctuations in your area? Yes. So what is the maximum fluctuations in your area? Participants, can you just comment? What is your maximum fluctuations in your area? See, we have selected like a 2 kilowatt is the converter rating, and output voltage 400 voltage and then 5 ampere is the typical rating. Yes. And efficiency we are trying to keep 90%. So we can go up to 98 also, but in that time you should select all the components as ideal components. So the getting that components is very difficult. And then input voltage regulation is about 15%. So here the 15% is nothing but generally instead of 230, so let us take so see here so here 230. So instead of 230, we may get either point 15 is the regulation, right? So 15 is the fluctuated regulations, 15%. So in that condition, 0.85. So this is the minimum voltage. Like 195 is the minimum voltage. In some industrial area, it may go up to 170 also, it may go. And the same way, 230 into plus 1.15, that is at 15%. So it may go up to 264. So now the point is that our power converter should respond when the input is 195, then the converter should supply a 400 voltage. At the same time, if the input is maximum like 264, that time also the converter should produce a 400 voltage 5 ampere current. This is the input regulation conditions, right? So is it clear? So have any questions? In this way only we are trying to regulate the circuit. Yes. So just give me a second. Let me take a file. See here See here, this is our typical sir. Please, sir, I can't get how 264 came. Okay. See here 264 nothing but 15% is the upper limit. See here we are claiming that 15% is the input voltage variations or fluctuations. So 230 minus 15% and then plus 15%. So by this method you can achieve that 195 and then 264. Right? I hope you got my point. So now so this is the inductance inductance calculation formula, and this is the capacitance calculation formula. See here the percentage of ripple nothing but that 0.15 is the percentage of ripple, or 15% is the one ripple, and VAC minimum square. So which is that VAC minimum square in the sense 15%. So here 230 minus 15% of the power supply. So in that case 195 is the minimum voltage. Same way, and then P naught is the power, and root 2 VAC minimum. VAC minimum nothing but 195 is the VAC minimum, and then V naught is the 400 voltage output voltage, and the T is denoted as a T is nothing but it's like a switching frequency. And a similar way for the output filter capacitor, and P naught is the power exact, power converter power, and 2 pi F line. So the F line denoted that line frequency, and delta V naught. So delta V naught denotes that the range of the fluctuations which we are trying to allow. So the range of the power, in the sense, instead of C, actually we assumed that we took reference as a 400 is the output voltage, right? So here let us assume, so 10% will be the tolerance of the converter. So in that case, 40 voltage will be the lesser voltage. So our circuit will regulate, fluctuate 360 to 440, all right? So that kind of regulation may get. So here you can get an option to keep 1% and then 0.5%. That also it's possible. That also it is possible. So now let us take calculations. Yeah. See here, we took a power as a 2 kilowatt and efficiency 90%, and then switching frequency 10,000 hertz, like a 10 kilohertz. And our assumed voltage is about 400 voltage. And then output is a 5 ampere. So how we are getting the sense, 2000 divided by 400 is the 5 ampere, right? And we input line voltage rated one is that 230, and the disturbance range 15%. And if you apply that one, then you may get a 195 is the minimum voltage. Sometimes in industrial area, it may go up to 20% also, right? So in that case, the automatic calculations you may require. So 195 voltage is the minimum and 165 is the maximum voltage, and line frequency 50 hertz. And now see, actually IS minimum, IS maximum, maximum and then minimum. So which is that if the line input voltage is minimum, in that condition the maximum output voltage, so that time also we have to draw. So here to get a maximum line voltage, line voltage is about 10.2 voltage. Similar way, minimum voltage will be like in the maximum side, the minimum current will be there. So the 7.5 is the minimum current, line input current, right? And then inductor value and be calculated with the help of the same formula. And capacitance value, again we are using the same formula. So here the range of the voltage fluctuations at the output side, we assume that 5% I can allow, right? So see here, for this for such kind of converter, you can go up to 10 kilohertz is the maximum switching frequency, because we are trying to convert 50 hertz to 10 kilohertz, right? So the input for the converter is the 50 hertz, and even though if it is a DC, that the ripple will be rotating at a fundamental frequency and then switching frequency. In between the frequency, the ripple will be there, right? So in this level, you may go up to 10 kilohertz is the one, but you can go up to 20-25 kilohertz also. But in that case, you may require a bulky inductor size, right? This is simple calculations. And then load value, R load, see the power, what about, B5 into B5, and then divided by B2. So B5 is the 400 voltage, and then, I squared R. So simply apply that value, then you may get a R value at here, right? So by simply implementing this one, then we are trying to model the block. So let us open the one. Yeah. So this is the simple boost converter circuit. Yeah. So just give me a second. Just give me a second, participants. Yeah. See here. Yeah. See here. This is whatever we modeled previous one, and then in the boost inductor value. And then this is the filter capacitor. Here we are added the filter capacitor, and then this is the load one. And we are calculating the output voltage and then input voltage, input current, right? And we not see, actually we have compared like a output voltage 400. So we scale down the entire graph into that scale down the value. So we consumed that, we take it as a reference as a 1 voltage. So we are matching the output voltage with the 400. So this is the actual one, and this is the this is the reference voltage, and this is the actual voltage. We are comparing, and then we are getting the PI value, so PID group. And a similar way, the input source voltage, right? So the source of the converter is that Vs, that is the measured one. And here we are applying, we are calculating the theta whenever it crosses that zero value. Whenever it crosses the zero value. So see here, so the input voltage will fluctuate sign, right? So now if you take a PLL group, PLL value, so here we should identify when, I mean, the theta of the phase controlled unit. And after that, you may get a phase cross sectional value. If you apply a sin theta, then you may get a one sin value, right? So if you if you apply a if you remove that negative value, then you may get a only the half of the positive one. And finally, that line inductance, line current. So this is the load, equivalent to the load current. And see here in the maximum calculations, so the current value will be like, just a second. Yeah. See here, the maximum current is about 7.5 ampere. So by just, you have to keep that value at this moment. You have to keep this value here. But after applying that value, by you may require some tuning method. So by that one, we achieve that 6.9 is the nearest value, right? So by applying this one, then you may get a reference PI value. Finally, you may get a PWM for this MOSFET. So by implementing this one, you may get a exact sign value. So let me open the graph. Sorry, let us remove that one. So now, participants, can you, can you see this image? Just a second. So now, see here, the same whatever we have applied, that 325 is the input voltage, and the inductance current is about 2.32 is the 2.32 millihenry is the inductor current. And the capacitance about 176,768 microfarad is the capacitor currents, and then current value is about 80 is the current value, right? And now, participants, if you have any questions, please ask me. I will try to give you. Explain the PWM controller circuit once again. Yes, sir. I will tell you one by one. So this is what I am trying to share you. Yeah. So people, can you just follow the model so that you may get clarified in detail? Yeah. And now this is the first block. This is the first block, like input voltage and then output, reference voltage, and this is the actual voltage, right? And so just to take the snapshot of the PID controller. So this is the PID controller. We took it as a reference. Source is the internal. We may get used, right? And this is the output voltage. Sorry, input reference voltage. And this block is the PLL block to generate, to identify the exact, phase cross section moment. So for that one, the fundamental frequency 0 and then 50 is the fundamental frequency. That the minimum frequency you can keep less than the fundamental frequency. Minimum frequency you can keep it less than the fundamental frequency. So like that you can take a block, and then sin function, and just take it as a square root to multiply it with the square root so that you can get a peak value, and then remove the negative phase. So by default, sign will generate a positive and negative, right? So we are trying to remove the negative one. So these two things can be multiplied, and in addition to that, so this is the line current or else the load current. So this current we are calculating from this one. Sorry. So see here we are measuring the line current. Let us run this one. Yeah, sorry. Yes, ma'am. So let me go through one by one. I will try to reduce that one. So now we are, now we are taking the line current. Before inductance, we are trying to model, sense that value. And after that, as I mentioned earlier, the line current is multiplied by the square root 3 divided by 6.9, right? Square root 3 divided by 6.9. This is the reference value, and this can be subtracted. This is the reference current, and this is the actual current. How we calculated here voltage is the reference, and then our actual voltage. Same way we are getting current, right? So this value again we are trying to take this value, proportional value and then integral value. So we took it as a trial and error based. So you can use that one also. Just take a snapshot. Yeah. So this is the here we may get a duty cycle reference. So this is simple PID, a PWM generator. The input based on the duty cycle, the PWM generator will generate a PWM. So this PWM can be applied. This PWM can be applied to the MOSFET. Right. So this is simple way you can you can build the system. So now you just try to model the same value. I will let me give you the solutions. And someone asked that let me answer your questions. IGBT specification. Yeah, I will tell you, ma'am, IGBT specification, how to select the IGBT for various applications. Also, I will tell you. Just engage the session. And then sir, actually, you have to build the model. So with the file will not be shared. So you just follow the instructions in the class itself. Whatever you have a doubt, I'm here to help you. But this is simple psychology. I will not share the file, but I'm here to help you. If you try to develop a model at this moment, I can get clarified your doubt completely. Yeah, please explain very slow. Yes, I will try to. And MOSFET details, this is default value I just selected, but in the Simulink, there is no any MOSFET model. But in the practical case only, we have to select a proper MOSFET, right? So participant, please follow please try to build such kind of model and try to run this one in your computer. I'm here to help you. Meantime, I will show you one more how to select, choose the components. Give me how to select the MOSFETs and IGBT for our applications. Yeah, parameter value, just take this parameter value. See the input voltage and see here the PID here. All the parameters are visible only. There is no any hidden parameters. Just to take the PID value only, inside value. So you just take a snapshot. So this is the first PID and this is the second PI value. So this we have used PI. Initially we have used PID method. Just use this one. MATLAB version, you can use any version, not an issue at all. Even MATLAB 2012 also may work. These are all the basic components. So participants, please, please model this one. We'll check, and meantime I will share you how to select the components. Just give me a second. I will take a note. Yeah. So participants, are you developing the model? If you are developing the model, just comment in the comment box. Rectifier specification, it's a common one. There is no any. Just use the default one. Rectifier, that is universal rectifier. Here, just change number of bridge arms to and then diode. That's enough. Anybody following that model, please comment in the comment box. Who are all developing the model? Participants, can you just comment? Who are all developing the model? I'm waiting for a reply. Who are all building the model? Okay. So now let us go for the analysis. Yeah. See here, this is the simple way. So at the initial stage, input current and then input voltage is not synchronized because of the filter capacitor. So we have not included the soft starting method. So that's why this current is, so this spike is happening. But when we include here we have to include that series capacitance along with the resistance, then we can reduce the, we can introduce that soft starting circuit that will help us to suppress the input current. Input current rise will suppress. So after the value, after some period only that the PID is getting to regulate the output voltage. So see here now, we are getting the input voltage and input current has been synchronized. The two things got synchronized, right? But before that one, it's not that value. See here, so these are all the unsynchronized area. So once if the loop get synchronized, then only we are getting the pure sine input voltage. So during this period, we are getting the input regulated power supply. and try to keep change the PID value, then we may get a 400 voltage as the reference voltage. I mean output actual voltage. That time we can call it as a regulated output voltage. That time we can call it as a regulated output voltage. The two parameter you may require to develop any kind of power supplies, right? You may require any kind of power supplies. If you have any questions, please ask me. I will try to give you the solutions. Or else just take a snapshot and build the circuit by your own. And if you have any doubt, you please ask me in the tomorrow session. I will try to give you the solution. So just take a snapshot, try to build the solutions. And here if I multiplied the sense, just for scale up the value, I multiplied 1. Just for scale up the value, I multiplied 1. This value. This is for the reference output. I mean, in the input current reference. Participant, just take a snapshot. Even I will also share the snapshot. But I will share in the chat box. Please practice this simulation and come up with the result for the tomorrow session. Is it clear, participants? Is it clear? This is very simple experiment. Try to build the simulation. Just to draw all the points. Even I will share you the values too. We have applied, and this is the inductance and the capacitance value. Please practice and come up with the model tomorrow class. All right, and then here you may require the PID value. Just to take a snapshot. I'm just going to share. So this is simple psychology. So people, if you follow, then you can easily develop your own controller. If you are facing an issue, I am here to help you, but you have to try. You have to try. And then there is no any, see here, PID controller, second PID controller. So here I used PI, not a PID. Just apply here. You can get, and then, so here all remaining and all default parameters. So just to take a block name. So these are the block name. Take a snapshot too. I will share it in the group, sorry, in the chat. So just build the simulation and come up with the tomorrow class. All right. Yes. So is it clear, participants? Is it clear? If you have any questions, please ask me. I'll try to give you the solution. If you have any questions, please ask me. I'll try to give you the solution. So now let's move to that device selection. See, we know that all the power control, power converter have an input voltage as well as that output voltage. See here in between. In the power circuit, we may use either SCR, triac, MOSFET, IGBT, GTO, or SiC MOSFET or GAN devices, right? So we help you to build a wireless power control, wireless power control power transfer circuit as a proof of concept, like a 1 kilowatt, 2 kilowatt system. Also, we will help you to build such kind of support. At the same time, we'll help you to build the simulation also, MATLAB simulation also. Suppose if you are anybody working in the PhD support, will help you. And same way for the how to select these are the devices. So let me tell one by one, and how to design a gate driver circuit, and how to choose the device for the target applications. See here, multiple devices are there. So let us check one by one, right? See here, as we know that all the MOSFETs or IGBTs are like a similar, like a typical mechanical switches, right? So when you apply a gate signal, then the depletion layer get vanished, and then the conduction has been started from drain to source. So by the time, so this is the gate current. So if the gate current keep on increases, then the source to drain to source channel has been established, right? So similar way, all the solid state switches are keep on working. So irrespective of all the controlled switches having that gate, any one of the gate terminal, if you apply a signal to the gate terminal, then we can get clarified. So AC to DC rectifier by default will use SCR, and again AC to AC will keep a triac model, and DC DC applications MOSFET is the ideal component. Based on the power and then kilowatt, power rating and frequency, we have to select IGBTs also for some time, not all the time. And DC to AC inverter will be the IGBT is the ideal device. Now how to go in detail. So these are the detailed different topologies of the various power control model, right? See here, for each and every one, SCR, So all the devices. So either, out of the 3 devices, you can select, but for this kind of topologies, so as we know, the power, switching frequency and then power kilowatt, power rating. So from these 2 data, we can select any one of the devices, right? So from this one, from the graph, you can easily identify. See here, we are getting that voltage ranges from 0 to maximum, right? 0 to maximum. This is the minimum value, and then this is the maximum value. So here we can vary. And the similar way, the switching frequency, right? The switching frequency from minimum to maximum, right? So see here, if you are developing a circuit, at this moment, see here the front end rectifier with a very low voltage, like less than 200 voltage, then you can select a MOSFET. Similar way, if you select a front end rectifier with like a mid range of the voltage, like 800 voltage, and then 100 more than 100 kilohertz, right? More than 100 kilohertz or nearby the 100 kilohertz. So here you have a choices between either IGBT or MOSFET. That in that conditions, you may require such kind of controller called See here the SiC MOSFET or GAN devices. GAN devices, it comes up with that gallium nitride devices, right? So either any one of the 2 devices you can select, right? So this is the basic thumb rule for selecting the devices. Either do you want to select IGBT or MOSFET? Participants, if you have any questions, so please ask, and then I will try to give you the solution. I hope you got the point. So tomorrow, for the tomorrow class, please build such kind of block, and then just download all the images, whatever I have shared with you, and then come up with the model output, and then tomorrow we will evaluate, right? If you have any questions, please ask me. I will try to give you the solution. Yes. So at this moment, I am just going to stop the class, and tomorrow we'll work for the motor control part. So we'll try to build the motor control for the DC motor, forward motoring, reverse motoring, forward in the motoring, forward braking, as well as the reverse braking. The 4 operations we'll try to build in the MATLAB Simulink. That is our tomorrow block. So participants, please try to practice the simulation and then come up with the preparation so that you can get clarified during the session. If you have any questions, please ask me. I will share the feedback. Please submit the feedback so that based on the feedback only, we'll give you, your attendance will get calculated. Just a second. I will take the feedback form. So the feedback form will be shared in the session. Just give me a second. I will share you. Yes, I will share you in the chat box. Just a second. Participants, so please submit your attendance. All of you, please submit your attendance. I shared in the chat box. I just shared in the chat box. Please submit. So based on this attendance, the organization team will share you the certificate. So please submit your attendance without fail. Thank you, participants. Thanks for your valuable time. And tomorrow we'll see. I hope you have got all the points. If you are if you are preparing building your solutions, then I am here. I'm also available in the group. Please post your query in the group. So don't be idle. I'm here to help you to complete the assignment. Right? Thank you, participants. Thanks for your valuable time. So now you can leave the class. So you just develop PFC converters Simulink, and then rating all the data we have given in the as a image. So please, participants, please download all the images. Keep it for your reference. So PWM, PWM controller. This is the PWM controller, the basic block. Please ask the question in the group. I am here to help you. Yes, I just posted. If you have any questions, if you need any support, please ask me. I will try to give you the solution. Participants, please come up with the results for the tomorrow class. I hope you have enjoyed. Please share your feedback in the feedback link. If you have any questions, please post the question in the query. I am here to help you. Thank you, participants. Thanks for your valuable time. And I hope everyone downloaded the images, whatever I have shared. These images will not be shared in the group, right? So those who have participated in the class, for them only that this kind of content will be provided. Thank you, participants. Thanks for your valuable time. Yes. So shall we close the session, participants? Shall we close the session? Or else, do you have any questions? Please ask me. Thank you, participants.